Suppose you were given two triangles, ABC and XYZ, and you were told that the two triangles were similar, so that AB to XY, two corresponding sides, had a ratio of 3 to 2. So, in other words, the scale factor between the two triangles would be 3 to 2. Can you figure out what the ratio of the areas would be? Would the ratio be the same as the scale factor, 3 to 2, or would it be something different? Well, to answer these questions, you have to continue with the video, because that's exactly what it's going to be about, finding the ratio of areas even when there isn't enough information to find the area themselves, like there is in this case. Okay, Ramblers, please take careful notes, and I hope this helps you understand section 11.7, the ratio of areas. Hey Ramblers, this video covers chapter 11.7 in our textbook and deals with the ratios of areas. What happens when you want to compare the areas of two figures, but you're missing one of the dimensions, like the height, or another dimension, like the base, and you can't calculate the area of the figure? Can you still compare their areas in a ratio? Well, this video is going to help you understand how you can. Now, be careful. This is probably the most difficult section in the chapter. So I want you to pause often, take really careful notes, and make sure you understand each of the 4 cases that I point out. I teach this a little bit differently than the book, but I think I break it down into different situations that if you can apply the rule to each situation, you should have no trouble with this chapter. All right, I really hope this helps. Good luck, and thanks for watching. Okay, as I said, there are 4 different cases when we compare two areas in a ratio. The first case is kind of self-evident, but I thought I'd include it just to be exhaustive. Case 1 says if we have two figures that are congruent, then the ratio of area 1 to area 2 is just equal to 1 to 1. Well, that should make a lot of sense. But let's take a look at an example. Suppose I'm given that triangle ABC is congruent to triangle FED. Well, that would mean that their bases are congruent, and that would mean that their heights are congruent. So the area of triangle ABC compared to the area of triangle FED is simply 1 to 1. All right, what's another example? Well, we could compare two circles. And if I know that the two circles are congruent, that would mean their radii are congruent, then clearly the area of circle O to the area of circle P will equal 1 to 1. All right, now that's pretty simple. Maybe we should move on to something a little more complicated. Let's take a look at case 2. Here we're told that the figures are similar. So to find out the ratio of area 1 to area 2, we're going to compare the scale factor, or the length of side 1 to side 2. But then we're going to square it. Okay, so this is very similar, or exactly like, the example that was given in the opener to this video. Let's take a look at why this is true. And we can do that best by an example. All right, say we had two triangles, triangle SML and triangle BIG, and we knew that the two triangles were similar to one another. Well, I'm going to start by looking at the dimensions of triangle SML. I can see that it has a height of 2.78 and a base of 10.97. And I'll look at the dimensions of triangle BIG. That has a height of 5.56 and a base of 21.94. So keep in mind, if we know that the triangles are similar, then I know that the bases are going to be in the same ratio as the heights are. If I can find the area of triangle SML, and I can find the area of triangle BIG, and 15.24 to 60.97, those numbers really don't mean too much to me. So let's try a different route. Let's take a look at the lengths of one side. Okay, well here we have some rounding problems going on because I constructed these two triangles so that one was twice as big as the other. So side SM is 5 centimeters and side BI is 10 centimeters. So really that means everything in these two triangles should be in the ratio of 1 to 2. So if I were to compare the ratio of their areas, you'll notice that the ratio of the smaller triangle to the larger triangle is 0.25. Now that might be a little surprising because the ratio of the sides is 1 to 2, but the ratio of the areas is 0.25 or 1 to 4. Why would the ratio of the sides be 1 to 2 and the ratio of the areas be 1 to 4? Well, the reason is the shortcut. And the shortcut says this, that just like I'm telling you in the formula here, you simply take the ratio of the sides and square it. So 5 divided by 10 is 1 to 2. 1 to 2 squared is 1 to 4, which is, of course, 0.25. Okay, but why is that? All right, well, let's take a look at an explanation and see if we can't figure out why all this is true. Well, it really comes down to this. If triangle SML is similar to triangle BIG, and let's say the ratio of the sides was x to y, or if you like as a fraction, x over y, then comparing the ratio of the two areas, even if we could calculate it out, we would calculate 1/2 the base times the height. But keep in mind, since the ratio of the two triangles is x to y, the ratio of their bases will be x to y, and the ratio of their heights will be x to y. So if we cancel out common factors in the numerator and the denominator, what we'll be left with is x times x over y times y, which can be simplified as x over y squared. But x over y squared is the same as the ratio of the sides squared. So that becomes our shortcut for finding the ratio of the areas if we know figures are similar. Area 1 to area 2 equals side 1 to side 2 squared. Make sure that's in your notes. That's very important. As you should also have the fact that when the figures are congruent, as they are in case 1, that the ratio is 1 to 1. Okay, let's move on. Case 3 is if the two figures share a dimension. So, for example, imagine we had a figure like the big triangle ABD, and a line or a segment is drawn from A to the base BD, dividing the larger triangle in half. I'm going to call them triangle 1 and triangle 2. What would the ratio of those two areas be? Well, we don't have any sides, we don't have a base, I don't even have a height. So how can I figure it out? Well, if I drop an altitude from point A to point T, that would be the altitude of triangle 1 because it's going from the base to the farthest vertex. It would also be the altitude of triangle 2 because it reaches from triangle 2's base to the farthest vertex at A. So if I were to compare the two areas, I would see that the area of triangle 1 is 1/2 BC times the height AT, and area 2 is 1/2 CD times the height AT. Well, if I cancel the equal terms in the numerator and the denominator, I'm left with BC over CD. I'm left with BC, this base of triangle 1, and CD, the base of triangle 2, which is what's going to give us our shortcut. If two figures are neither congruent, which is case 1, or similar, which is case 2, but they are both the same type of figure, then the ratio of their areas is the same as the ratio of the non-shared dimension. In other words, area 1 to area 2 will be the same as the ratio of the non-shared dimension 1 over the non-shared dimension 2. What does that mean? Well, in our our brown triangle and green triangle shared a height. So in order to figure out the ratios of the areas, we compared the dimension they didn't share, which was the base. Okay, that's an important shortcut. Make sure it's in your notes. All right, let's move on to the last case, which is when there's really nothing going on between the two figures, like we're comparing a circle and a rectangle. They don't have to share a radius because obviously a rectangle doesn't have one. So if the figures are not congruent, they're not similar, nor do they share a dimension, then there is no shortcut. You simply have to calculate each area separately and compare them. That might be a little obvious, but like case 1, I wanted to be exhaustive. Okay, we need to take one more look at a theorem that comes up in this section, which looks a lot like case 3, but it deals with the medians of triangles. Theorem 110 is a pretty handy theorem, and it tells us that if a median is drawn in a triangle, then it divides the triangle into two new triangles that have equal area. Okay, well, why is that? Well, I'm going to draw a median AD. Now, as you recall, if AD is a median, that means that D is the midpoint. So BD is congruent to DC. Well, it's going to divide into two triangles. I'll call them triangle 1 and triangle 2 for simplicity. Now, triangle 1 will have a height of AE. That will also be the height of triangle 2. So if I were to calculate the areas, area 1 to area 2 would equal 1/2 the bases, which is BD for triangle 1 and CD for triangle 2, times the shared height AT. Now, this is a lot like case 2. They share a height, so we should compare their bases. Well, in this case, since AD is a median and D is a midpoint, BD is congruent to CD. So therefore, the ratio of the areas is going to be 1:1. But maybe it's easier just memorizing the theorem, which says a median divides a triangle into two triangles with congruent areas. Okay, Ramblers, a couple of tutorials to look at to help you with the exercises in this section. This is a really tough section, so don't be afraid to go back through this video and review your notes. Okay, thanks for watching, and I hope this helps. Okay, number 10 on page 548 kind of brings in all the concepts and shortcuts that we learned in this video. So let's take a look at letter A. They ask us to find the ratio of the area of shaded to whole. So the shaded and the whole triangle are similar. And now keep in mind, we're not comparing the shaded to the unshaded. It's the shaded triangle to the big triangle. Now, since those two lines are parallel, I know that these two triangles must be similar by angle. And so I'm going to use case number 2. Now, you recall case 2 told me that I simply compare the ratio of the corresponding sides, which would be 2 to 2 plus 7, and square it, so that I get 2 to 9 squared, which is, of course, 4 to 81. Okay, let's take a look at B. In part B, we have two triangles that aren't similar, but the shaded to the whole appears that they share a height. So since they share a height, I'm going to compare the bases. So one base is 2, and the whole base is 2 plus 7, so the ratio of the areas is 2 to 9. All right, let's take a look at C. Letter C is also like case 3. They don't share a height, but clearly the shaded triangle and the whole triangle share the base. So I'm going to compare the heights. And the height of the shaded triangle is 1/3 the height of the unshaded or the whole triangle. So the ratio of the areas is 1 to 3. Now, in letter D, I can see that the shaded triangle is similar to the whole triangle. So I'll compare the square of the corresponding sides, which is 12 to 18 squared, which you should reduce before squaring. so that you get 2 to 3 squared, which equals 4 to 9. All right, Ramblers, you'll have some other practice with this, but please go through this again if you need to. Thanks for watching.